Good morning, good afternoon, and good evening to everyone who's tuning in. Welcome back again. And now we have Dr. Rita. Dr. Rita is an assistant professor at Texas A&M University, specializing in the application of oil and gas skills and techniques to address challenges associated with low carbon energy technologies. Dr. Rita earned her PhD in energy resources engineering from Stanford University, where she also had her postdoctoral training. Prior to pursuing her doctorate, she was a principal reservoir engineer at SLB, where she worked with for 13 years. During her tenure, she contributed her expertise to various product lines and locations. Her current research encompasses geothermal reservoir engineering, carbon dioxide storage and utilization, geologic storage and generation of hydrogen, and reservoir geomechanics. She was a Society of Petroleum Engineer 2023-2024 Distinguished Lecturer, during which she lectured in 12 countries in 16 sections on how oil and gas competences are shaping low carbon energy technologies. She is also an author of 2 fiction novels. Thank you so much, Dr. Rita, for coming today, and we're so happy for having you. The mic is yours.
Thank you very much. It's my pleasure to be here to be talking about the future of hydrogen energy. I wish I had a crystal ball to talk about the future of hydrogen energy, but I will just talk about what I'm seeing and just my perspective and my opinion. So I will start with introductory concepts to hydrogen, especially because my understanding is that I have a high percentage of students on this call. I will then look into hydrogen sources and conversion processes, storage and transport, risk, safety, cost, and then bring all these things together to look at the kind of challenges we see, the solutions that are out there that should be driving the future of hydrogen. I've been introduced, but in the event that you want to connect with me afterwards, because I may not be able to answer all the questions in 10 minutes, please feel free to reach out to me on LinkedIn and connect with me, okay? So introductory concepts to hydrogen. So why are we talking about hydrogen? So I'm going to take us back a little bit to be looking at the evolving energy mix. Maybe you've already seen this slide before. But the key thing to take about this slide is that as time has been progressing since the 1800s, the energy mix has been evolving. And so it's been changing in different percentages of different sources of energy. In the earlier years, what has been the main driver for, replacement of one fuel source over another has been scarcity or high prices. So demand and supply has driven a lot of it. But more recently, what we're beginning to see is the need to reduce greenhouse gas emissions and utilize the resources that are closer to us, okay, with minimal environmental and social impact. So the drivers for the kind of energy mix that we are having now and moving forward is driven no longer solely by demand and supply, but energy security, not impacting our environment socially and environmentally. So in a broad sense, we look at different sectors that have utilized fuel before now and the associated emissions with them. So this figure shows different sectors. So we have industry, electricity, agriculture, transport, and buildings, to look at their percentage contribution of emissions. And the reason why it's good to look at it from this perspective is because that way, if we're trying to look for solutions to address emissions, we could actually go on a sector by sector basis. Okay. Let me see if I can remove this stuff here. Okay, all right. So with that, when we think about pathways to decarbonization, we see things like when we look at buildings, for instance, we try to think about ways in which we can reduce emissions towards buildings. And so we have energy efficiency and conservation approaches. When we think about the transport sector, we could either think about electrification or using cleaner fuels. Then we look at the agricultural sector and we think about how we can make changes to our land use to reduce emissions. And then we have things like carbon removal and carbon capture, utilization and storage that addresses maybe a mix of different sectors, especially electricity generating sectors, power generating sectors. Then fuel switching comes when we consider replacing a source of fuel or energy that we have with something else that is low emitting or zero emitting in terms of greenhouse gas emissions and carbon. So the question is, where does hydrogen come in all of this? So let's start with, why should we even be having hydrogen? So we think about hydrogen in the context of the hydrogen economy. And what we're trying to say here is that we're beginning to replace different parts, sectors of the system where we would have been using all the other sources of fuel that may be generating carbon. So we kind of replace those systems with hydrogen. So we'll find it in things like our industries, we'll find it in electricity generation, we'll find the use of hydrogen in transportation. So that's basically what a hydrogen economy is all about. If we can find ways of replacing those other fuels with hydrogen, then we are successful in our hydrogen economy. So why hydrogen? It's considered the most abundant element in the universe, and it exists in many forms. So quite recently, or prior to now, a lot of thoughts about hydrogen was it didn't exist on its own, and it exists in combination of other materials or elements. But we are beginning to see that we could have hydrogen in the subsurface, which can exist by itself. So hydrogen carries an exceptionally high energy content by weight, and I'm going to have a slide where I discuss some of the terminologies that I'll be using. So I'll explain what that is. And then when we combine hydrogen with oxygen in a means to do combustion, we do not yield particulate emissions or carbon monoxide, because this reaction between hydrogen and oxygen yields water. We can integrate hydrogen with our renewable energy markets, and I also have a section that looks at the fluctuations in some of the renewable energy sources, like when we have highs and lows, seasonal times of the days when we have more of solar versus other times of the day, and how we can integrate hydrogen as a carrier or as a storage mechanisms for complementing renewable energy. Well, beyond energy, hydrogen is a feedstock that has various other consumer applications. In today's talk, I won't be able to go through all the applications and uses of hydrogen, but I will do well to point you to the direction of where you can see this in detail. So in terms of terminology, the kind of things that you might be hearing, I might be throwing out these words. I just want to lay a foundation. Hydrogen is that chemical element with the symbol H and atomic number, where if we do recall our periodic table, it's at one corner of the periodic table. In the context of energy, it is considered a clean energy carrier that can be used as a fuel for storage and other industrial processes. When we talk about energy, it's the ability or capacity to do work. And if you see any slide of mine that is saying something in joules, kilowatt hour, or megawatt hour, it means I'm talking about energy. When I divide my energy by time, I have a rate. So power is the rate of doing work or expending energy, usually measured in watts. Now, if you see my slide with something like joule per second or watts or megawatts, I'm dealing with power. I'm talking about power. And then renewable energy will come a lot because hydrogen is trying to, is a way to complement our renewable energy. And so that is the energy that is supplied from a renewable source like solar, wind, geothermal energy, hydropower, or any source that is easy to replenish. As we're taking that source out for use, it's being replenished in the subsurface or where it's coming from. Greenhouse gases are, the things that we say when we're talking about emissions. We know there's CO2, carbon dioxide emissions, but it's just part of the different greenhouse gases that have a way to trap heat in the atmosphere. And so we would have methane, nitrous oxide, water vapor, and some fluorinated gases in addition to carbon dioxide. When we talk about net emissions, it's looking at the overall balance, like how much in and how much out. So we talk about net zero emission is trying to say that whatever that I put in terms of greenhouse gases, I should be able to take out of the atmosphere. Okay. And then the energy density is the energy stored in a given system or substance, and we could have it as a unit of volume or mass. So I have energy, but I am measuring this energy as a function of volume or as a function of mass. So that's my energy density. And so we have two types of energy densities, and I will explain that in subsequent slide. And then an energy carrier is a substance that can store, transport, and deliver energy. You may be converting energy from one form to this energy carrier and then later on retrieving your energy. So hydrogen is an energy carrier. In this case, we are able to derive it from renewable or low carbon energy sources without producing significant harmful emissions or pollutants. Some of the properties of hydrogen that should be of interest. So it's a colorless, odorless, tasteless gas, non-toxic. It's highly combustible, okay? And this figure here shows what it is when we look at the phase diagram. So on the y-axis, we have pressure, and on the x-axis, we have temperature. And you can see that these temperatures are sub-zero. So it means that anywhere to the right of this temperature is going to be the normal temperature where we operate, okay? And what it means is that at low pressures, normal conditions, everyday conditions, hydrogen is going to exist as a gas. If I want to change it from a gas to a liquid, I need to go to a temperature that is very, very low, about 243 degrees C or so. 240 degrees C, which is at this critical point, okay? And then if I'm below 13 bar, I'm also going to be in this phase, this liquid phase. Now, if I increase my pressure above that 13 bar, then I'm going to have a compressible liquid. And this piece of information is important for us to know how we can store and transport hydrogen. In terms of its density and viscosity, the figure on the right compares hydrogen with other gases like methane and carbon dioxide. And we can see that the density of hydrogen is quite low. It's very low compared to the other gases. In terms of viscosity, the viscosity across different pressures and temperatures is almost constant, okay? And it's also very low viscosity. So what this means is we do have hydrogen having a high gravimetric energy density. That means the amount of energy contained in 1 kilogram of hydrogen is quite high, 120 to 142 megajoules. But because of its low density, I have a low volumetric energy density. Because this volumetric energy density is the multiplication of this gravimetric energy density times the density of the gas. So this low density then reduces the volumetric energy density. Okay, so it means that I will need a lot of volume to be able to generate the amount of energy that perhaps methane will do. So I will need much more hydrogen in terms of volume to generate energy compared to something like methane because of the density. So when hydrogen bonds and we generate flames, it's almost nearly invisible to the naked eye. In fact, there's a joke that hydrogen can be burning and somebody can walk into a hydrogen fire. Okay, so we need to find special ways of trying to identify when we have a hydrogen fire. So let's look at energy sources for hydrogen and how it's converted. So this figure that is over here is showing the hydrogen value chain. So we go through the process of getting the hydrogen, or we have a source for which we can use to convert or derive hydrogen through several processes. And then from there, we are either going to utilize the hydrogen or store it. We can also convert it into something before it is transported, and there are different ways of transporting this. Now, over here, I have natural hydrogen. So with natural hydrogen, I don't need to go through a conversion process to get the hydrogen itself. Okay, but in all these other ones, renewables, nuclear, natural gas, petroleum, or bioenergy, I need to go through a conversion process before I get the hydrogen. The current uses of hydrogen, and this keeps evolving as technology evolves. Some of the things that are listed here are, they are not in, high development phases. Some of them are in early testing and development phases. In other cases, especially in the industry, we have a lot of uses of hydrogen. So at your convenience, feel free to visit this YouTube link to get an explanation of the different ways in which we use hydrogen. But the main thing is that the use of hydrogen in the industry has grown since 1975, and associated with it is also high amount of CO2 generation, that's carbon dioxide generation. So how do we produce or generate the hydrogen? So if we are not having natural hydrogen, there are different ways. We could get it from fossil fuels or from renewable sources. And within fossil fuels, a very common method is the steam methane reforming, which I will talk about today. And then I'll also talk about from renewable sources, when we split water into hydrogen and oxygen, it goes through the process of electrolysis. And within electrolysis, there are different methods of electrolysis. So the alkaline method and the PEM, which uses a membrane, these methods are more advanced, while we have the solid oxide and a couple of others that are still being tested and getting into commercialization phases. So three key methods, pathways for generating hydrogen, which is not a natural one. We have the steam methane reforming. And what happens is that we get natural gas and we expose it, we bring it in contact with very high temperature steam. And this creates a synthetic gas, which is a mixture of hydrogen, carbon monoxide, and in some cases, small amount of carbon dioxide. Now, with this carbon monoxide, if we further expose it more to the steam, the high temperature steam, we are able to get hydrogen, and then carbon dioxide is also produced. Okay, so there's a whole process where we go through, we have a water shift gas process, we have the PSA pressure shift adsorption processes. So this is a process that is well known and has been used a lot for generating hydrogen. With gasification, we would be dealing not with natural gas at this point, but with something like coal or biomass. And we have high pressure steam and oxygen. It's not a process that goes through complete combustion. So we form this syngas, the synthetic gas that contains hydrogen and carbon monoxide, and then further reaction with steam brings about the production of hydrogen. In the case of electrolysis, we use electricity to split water into hydrogen and oxygen. And so if the electricity source is a renewable energy source, like solar, like wind for geothermal energy, then we say that that's a clean hydrogen, okay, or green hydrogen. But we'll talk about colors of hydrogen later on. And so these sources of hydrogen from a renewable energy source or a low carbon generating source has a lot of benefits for the fact that it's not a process that emits a lot of CO2. The steam methane reforming and gasification processes have a lot of CO2 associated with them. I bring in fuel cells here. It's not a way of generating hydrogen, but it's one of the ways of utilizing hydrogen. And in this case, it's, it comes from a similar principle as the polymer electrolyte membrane that was being used in electrolysis. But now, instead of creating the hydrogen, it's utilizing the hydrogen to generate energy. So like the reverse process. And so we can use this in things like vehicles. And so you hear of hydrogen fuel cell vehicles, where we have this fuel cell stack that embedded in it is this membrane that would be able to utilize hydrogen from a source to generate energy. And this energy is what's going to be used to run the car. Now, speaking of natural hydrogen, there are several instances where natural hydrogen itself has been identified, coming from seeps beneath the earth or being found in some reservoirs, okay? So the figures 1, 2, and 3 are mostly, how we define the ways in which the hydrogen is generated. So this first one is based on radiolysis. Is a combination of water with some of the radioactive elements in the subsurface to release hydrogen. We have serpentinization, in which case water comes in contact with olivine-rich rocks. And these rocks, through this process, the chemical reaction that takes place, hydrogen is produced. Or deep-seated, I can't really say exactly what's going on below this point, but we do know that from deep-seated origins, we've had hydrogen. And what this figure also shows are pathways in which we could lose some of the hydrogen that is generated, and which might be some reasons why, if we do go into some places where we expect to see hydrogen, we don't see a lot of it. And that's because hydrogen is such a small molecule, and it could pass through very small seeps. It could pass through, any pores, seeps, and things like that. Okay. We could also have microbial consumption of the hydrogen. So there are actually some microbes that could eat the hydrogen. They feed on the hydrogen. And so when the hydrogen is generated, they are eaten up. And so these are seeps in the surfaces. And at the bottom, we could have some abiotic consumptions as well. So how do we extract this hydrogen? We should be able to find hydrogen that should be, accumulated somewhere and then trapped. And then if we could drill wells down to those locations, we should be able to find the hydrogen themselves. Or we could go to those, if we have access to hydrogen-bearing rocks, where the hydrogen is being produced or generated, we could access them. Or we could try to enhance it by, stimulating it, creating some additional reactions that could speed up the process of hydrogen being generated. So this figure here shows that there are several locations worldwide where natural hydrogen discoveries have been found of different quantities or concentrations, okay? So this figure doesn't tell exactly the amount of concentrations per locations, but what it shows is that the hydrogen concentration was more than 10%. So one way that we've looked at the different ways in which we could generate hydrogen, but this process of serpentinization, where we have the reaction of water with olivine-rich rocks, is something that is easier to replicate if we do have access to olivine-rich rocks, okay? And when we look at the purity of the hydrogen that could be generated, this slide here tends to show that it varies. It varies with location. So recall that the other figure I showed 2 slides away was looking at hydrogen greater than 10%. But if we really drill down into natural hydrogen in accumulations, major seepages, and ophiolite complexes, we would see that we have varying concentrations of this hydrogen. And there are several reasons why, because depending on the source rock and the pathways, we could have different ways of different things that will be produced alongside the hydrogen itself. And this is depending on what are the gases existing, the method of reactions, if we have different geothermal gradients and pressure conditions, and if there's any external contaminations. This equation in green basically shows a simplified way in which we could generate hydrogen. So we have olivine-rich rock coming in contact with water at the right conditions should be able to produce serpentine and release hydrogen. And this is what we are looking for from natural hydrogen systems. And if it's possible, we could engineer these systems if we're able to find these olivine-rich rocks through the use of catalyst, thermal stimulation, hydraulic stimulation, or biostimulation, and a combination of all of them. But the key thing is that even if we generate it, we need to have where it can be accumulated and trapped so that people can later go back, drill wells, and assess this trapped hydrogen or accumulated hydrogen. The different colors of hydrogen, it all depends on how it is produced. So we have the green hydrogen, and that is produced from the electrolysis of water using renewable sources. I would go to the gray and the brown because the gray one comes from steam methane reforming. When we go through that process, we produce CO2, carbon dioxide, from steam methane reforming. Similarly, if we go through the process of gasification from coal, we also produce CO2. Now, if from these two processes, we are able to capture the carbon dioxide and store it or use it, then we have blue hydrogen. We have the purple or pink hydrogen, that is hydrogen produced by electrolysis using nuclear power. We have the turquoise hydrogen based off hydrogen methane pyrolysis. And then there's yellow hydrogen when we use electricity from the grid to go through the process of electrolysis. So we aren't going directly to wind or solar or any of the renewable energy sources. We're using the grid energy, okay? Power from the grid. And then there's white hydrogen, which I usually would refer to the natural occurring hydrogen. Okay. So how do we store hydrogen? Okay. So if you recall the phase diagram looking at the pressure and the temperature, you would see that we need either very low temperatures to be able to change the phase of hydrogen from gas to liquid, or we need very high pressures to compress the gas. And so in physical-based methods, we could either compress the gas by increasing the pressure, and so we have high pressure tanks for that, or we have to reduce the temperature way below it's way below 240 degrees C, okay, and convert it from gas to liquid. We could combine it, pressure and temperature, to get the cold cryocompressed gas. There are also some materials that could be used to store hydrogen, which most of them are also in testing phases, may not be as large scale. Some have proven successes. But basically, it's based on the principle of adsorption, where the solid hydrogen attaches to the surface of the solid, okay, and is stored there and can later be extracted by changes in conditions like pressure and temperature. or within some solids through absorption. But when we begin to think about large-scale hydrogen storage, then we have to think about using the subsurface, which comes with pressure, and pressure helps to do this compression part of things. So in terms of subsurface storage, we use things like depleted fields. So these are fields that we may have used to produce gas and oil. And after we've produced those fluids, we have some space and we can inject hydrogen into them. Preferably gas reservoirs, because oil can lead to contamination of the hydrogen. We have what we call salt formations or salt caverns. We could, go into salt formations, drill a well, use water to create a hole in the subsurface, and then this hole that is created is where we later on inject the hydrogen. Or we could inject the hydrogen into saline aquifers. So these are reservoirs of water that we would not use as groundwater or as drinking water, but we find them all over the world, and so we could store hydrogen there. Now, there are a couple of challenges that come with this, and so we have to be careful in our site selections to know which fields will be best to store large quantities of hydrogen. So today I was teaching my class about hydrogen, and I was asked, why should we store it, or how does it come about? And this figure here is looking at the wind and solar curtailment of California between 2014 and 2021. The first thing we see is that curtailment is increasing, and that is happening because we are adding more of these renewable energy sources. But the thing is that we've increased the capacity for the renewable energy resources, but there are times of the day when they are not needed as much, or seasons within the year where they are not needed as much. And those excess energy or power, the excess energy that they are able to produce, but they are prevented from producing, is what we would call the curtailed energy. And this has been increasing. And so we have to think about within 2020, for instance, we can see where the curtailment was very high, which means there was a time when we had to prevent the production or distribution of this power coming out of the wind or solar plant. And then at some point, this curtailment was low, which means we probably were using more of the wind and solar energy. And in terms of storage globally, most depleted reservoirs have been used to store natural gas. So there's an experience with it. There's also aquifers, and then there are also salt rocks. Okay. So this figure on the right tends to show that if we do have this kind of seasonality, which are wind and solar energy, there will be times where we can take the curtailed energy, convert it to hydrogen through something like electrolysis, and store it. And then there will be other times when the curtailment is low, sometime here, sometime here, and we have need for this energy, we can bring it out. And so this goes on in cycles, okay? And so these periods are when we're using curtailed energy, storing it, and this other part is when we're utilizing the hydrogen. So you can take this hydrogen, convert it back to electricity by passing it through a turbine that could use the hydrogen. So over here, I share some pictures, a list of some of the projects worldwide released. I know that there are much more than these, but this is what is available in literature. And the figure on the left here is looking at if I take my energy from a solar or wind plant and I convert it to hydrogen and I store it and I later bring it back up and try to generate hydrogen, I have only 35% efficiency on average. And in order for me to move up to 100% efficiency, I need to improve on certain processes, like how am I withdrawing my hydrogen from where I stored it? What is the efficiency of my turbine? We don't have 100% turbine efficiency, but if I could, imagine if I could increase it, it has this impact. And the method in which I'm converting my energy from my solar or wind to hydrogen using an electrolyzer, if I can improve my efficiency to somewhere around 33 kilowatt hour per kilogram of hydrogen, I should be able to improve my round trip efficiency. But overall, improving my electrolyzer efficiency is going to help me to improve the amount of hydrogen that I can get from my power to gas to power process. Now, transportation is another thing we think about. How do we transport hydrogen? Because it's if we want to have a hydrogen economy, we need to be able to have this hydrogen move to the places where it's needed. So there's the possibility of using pipelines, converting the hydrogen into ammonia, liquefying the hydrogen with reducing the temperature, or storing the hydrogen as a liquid organic hydrogen carrier. Okay. And this figure here tends to show the different pathways. So there's pipeline routes. There is the pathway for using ammonia. So you have to make the ammonia react, the nitrogen react with hydrogen to generate ammonia. And then when you reach your destination, you crack the ammonia to get your hydrogen. When you do your hydrogen liquefaction, cool it down at very low temperatures. When you get to your destination, you vaporize it to get your gas. And then if you have a carrier, so you go through the process of hydrogenation, your hydrogen is contained in there. And then once you get to your destination, you go through the process of dehydrogenation to extract your hydrogen. So all of these processes are energy intensive in one way or the other, either through cooling or either through the conversion process, but they all have different energy requirements. So let's look at some questions. One question that I usually get is, isn't hydrogen going to explode? If we have a hydrogen economy, isn't everything just going to explode? So granted, hydrogen has its properties that, it combusts quite easily. It has a lower ignition energy than gasoline or natural gas. And when it burns, it's nearly invisible. So it might not be easy to identify. And it has what we call a wide range of flammability concentrations in air. So it'll be flammable over a wide range of hydrogen concentrations. But it poses this safety risk and hazard, and it's something of concern. But the good thing is that there are other industries that have been using hydrogen. And so there are lots of safety protocols that have been put in place. And as we try to think about a hydrogen economy, we would be thinking about how do we incorporate those lessons learned from the different industries? How do we implement it as we make it scale? What kind of detections do we need? What kind of measurements should we be taking? What kind of pressures and temperatures should we be operating? And be thinking about our fire triangle. What do we remove such that we don't have hydrogen combusting? So this picture is basically showing an example of there is a hydrogen fire here. You could feel it, but it's not something you can see. So this is propane flame in daylight versus hydrogen flame in daylight. And so we use some kind of thermal sensors to be able to identify hydrogen. Okay. Another challenge with hydrogen comes from its compatibility with materials. And so anything we're going to be using, the pipelines, wellheads, storage tanks, we need to be sure they can withstand hydrogen, because at certain pressures and temperatures, hydrogen can cause embrittlement. It will weaken the metal. It will diffuse into the metal and weaken these metals. And so when that happens, we could have structural failures. Okay, and that's something we want to do. We want to have when we're talking about a hydrogen economy. So your pipelines, your storage tanks, and all of these being affected by the hydrogen. But an interesting thing is We do have ways of material selection. We also know what are some pressures at which we are going to lose the strength of our materials. So proper design, material selection, though expensive, would help us with hydrogen, overcoming the hydrogen compatibility issues. Some other issues with hydrogen is different pathways produce high intensity of carbon. And so we should be thinking about what are the ways in which we can reduce the carbon intensity of hydrogen. And then cost. Different methods of producing hydrogen comes with different costs. So it's most likely we're having a trade-off, high cost for low carbon intensities and low cost for high carbon intensities. So the key is, where can we get low costs and low carbon intensities, and can we make things like natural hydrogen a reality? Okay. So the demand for hydrogen is expected to grow, and we expect that hydrogen will be used in several parts of the industry, have other uses. And so again, this is what is going to be driving this hydrogen economy. And so for us, what we need to think about is, how do we scale up our low carbon intensity hydrogen sources? What kind of technology advancements do we need to improve efficiencies? As we could see, the conversion of power to gas wasn't giving us the kind of efficiencies we need. So how do we improve the efficiency? And then we need to think about what kind of policy support would help us, to do research, to drive down, to scale up some kind of technologies that are needed, okay, just to support the economy for hydrogen. So I think I should be stopping now and leave room for questions and comments. So thank you very much.
Dr. Rita, thank you very much. Do you prefer to read we have like 8 minutes. Do you prefer to read some questions from the Q&A box?
Okay. We have about 26 questions or so, and we would need to, maybe I'll need to copy them.
I will do that for you, just to answer questions for 8 minutes.
Let me see. I will go through the questions very quickly. And let me see if
there's questions and there's some in the chat also.
Yes, I'm seeing them. So I think one of the questions, how does hydrogen complement things like solar, wind, and all those ones? And what I said was that when we have periods of curtailment where we need to curtail those energy sources, we can take them, convert them to hydrogen, and then later use. So hydrogen would be complementing renewable energy sources. How do we assess the long-term sustainability of these methods in terms of efficiency and carbon emissions? So technologies like steam methane reforming have been there for a long time. We've had a lot of experience with them, and they're sustainable from a point of knowledge of the technology. However, they are associated with high CO2 production generation. And so when we combine them with things like carbon capture and storage, we're able to reduce the CO2 emissions associated with it. And we do have net zero emissions. If we can achieve that, then that makes those technologies more sustainable. Let me see. So one of the uses of hydrogen is in something like steam manufacture, where we replace coal with hydrogen, and hydrogen acts as a direct reducing agent, and we're able to have green steel production. So that's one of the ways in which we could use hydrogen. Another way in transportation is in fuel cell electric vehicles. So we also have that. Let me see if I can go through other questions by another person. What is the life cycle environmental impact of hydrogen fuel cells compared to traditional fuel cell technologies? Okay, so when it comes to the life cycle assessments. I haven't done that personally. I don't have that number off the top of my head, but I can check that. But if it's just basically in the fact of using hydrogen in the vehicle to combust, we are not going to be generating we won't be generating CO2 in the vehicle that is being used. Okay. So in terms of profitability, I'm sure I talked about the cost. And so if you have time, you can look at the figure, the chart on the cost. So renewable energy resources, they are more expensive than steam methane reforming, but they have less carbon intensities. Is it possible to synthesize olivine industrially? I won't say anything is impossible, but when we think about, the components we're going to be bringing together, the kind of energy requirement, I think it would be better to assess or utilize the olivine in the subsurface to generate hydrogen. Ahmed, someone is asking for a video of this presentation, and I'm sure since it's recorded, there will be a way for it to be shared. Okay. So someone is asking about the rocks from which we get hydrogen. So they are known as ultramafic rocks, for instance, or olivine-rich rocks. And I don't know if this question was asked before I presented my slide that showed the olivine-rich rocks. Okay. So the main technical challenges with green hydrogen production. So you see, the process is electrolysis. So we have efficiencies of the systems who are electrolyzers who are using membranes. We have what we call platinum that is also used for the stacks where we're going to have these membranes. We also have issues with the amount of water that we're going to need to be able to split to generate the hydrogen. So there are several things that are involved in developing green hydrogen. And if we can, improve on the efficiencies of converting, not using so much energy to generate 1 kilogram of hydrogen, that will be very good. Okay. So there's a question, how stable is hydrogen when compared to CO2 when stored in the subsurface? So hydrogen, while it reacts, well, from the kind of studies that I have done personally and compared with CO2, I don't see much reaction between hydrogen and something like sandstone in the reservoir. I see more of that. I see things like mineralization with CO2 than hydrogen. Okay. Now, in terms of when we inject it, how does it behave? My expectation is that hydrogen is going to move a lot faster and away from where I'm injecting it compared to CO2 because it is highly mobile. And then the other thing that I see is it's more buoyant. So what it means is that when I put it in the subsurface, it's going to be tending to rise up. Whereas for CO2, if I have sufficient pressure and temperature, I can get my to be somewhere less buoyant. But with hydrogen, it's difficult to make it less buoyant because it has very low density. Okay. So how cheap is hydrogen to solar, wind, and other renewables? So the question depends. So if I'm dealing with natural hydrogen, then natural hydrogen is cheap. But when I'm talking about the hydrogen coming from solar, wind, and other renewables, it may be more expensive because I have to use that energy from those sources to go through the additional stage of converting it or splitting my water to generate hydrogen. So what is the advantage of using hydrogen over natural gas? And so it's mostly two things. One, the gravimetric density. So if I have 1 kilogram of hydrogen compared to 1 kilogram of methane, 1 kilogram of hydrogen will give me more energy. The second thing is the combustion process. If I take hydrogen and react it with oxygen, I'm going to be forming water. However, if I take methane CH4 and react it with oxygen, I'm going to be having CO2 plus H2O. And so I'm going to be producing carbon dioxide. And we are trying as much as possible to reduce the amount of carbon dioxide that is being produced. Okay. I think I am at time. I don't know if there's any way that I could get the remaining questions, then I could see how I could answer them and maybe post them on LinkedIn or something. Okay.
Dr. Rita, I already copied all the questions, so I will email them to you.
Okay.
Thank you very much. This was great presentation, as usual.
Thank you.
Thank you very much for accepting our invitation.
My pleasure. Thank
Very
you.
good. Thank you very, very much.
Yes, thank you very much.